Hello there, welcome to Ethio-Hahu tutorial. I'm Ethio and today I'm going to discuss about heat energy. If you are new to this channel, like, subscribe and share. Today's lesson is about heat and temperature. Let's see what temperature means and what heat means. Temperature is simply a measure of average molecular kinetic energy of a system. If we know the temperature of a system, we know the average molecular kinetic energy of that system. Also, temperature determines the direction of heat flow. Always heat flows from a region of high temperature to a region of low temperature. Therefore, temperature determines the direction of heat flow. In some cases, we can also define temperature as a measure of hotness or coldness. By measuring the temperature of a system relative to any other system, we can say that system is either hot or cold. But the formal definition of temperature is a measure of average molecular kinetic energy of a system. We'll see how kinetic energy of a system is directly related to that of temperature. When you come to heat is a form of energy that can be transferred from one point in space to the other point in space as a result of difference in temperatures. If two different systems are at different temperatures, heat will flow from a hot substance to the cold substance. As I have said earlier, temperature determines the direction of heat flow. Therefore, heat flows from a region of high temperature to a region of low temperature. If two systems are at different temperatures, heat will flow from one system to the other. Let's consider two systems at different temperatures. System 1 at temperature T1 and system 2 at temperature T2, and they are brought in contact. If temperature T1 is greater than temperature T2, heat will flow from system 1 to system 2. That means, since temperature T1 is greater than temperature T2, heat flows from system 1 to system 2. This net heat transfer, persists until they have same temperature. Once they have same temperature, the temperature of system 1 and the temperature of system 2 becomes the same, and that condition is said to be thermal equilibrium. Until thermal equilibrium is reached, net heat transfer occurs from a region of high temperature to a region of low temperature. This is the direction of heat flow. Heat flows from a region of high temperature to a region of low temperature until they have same temperature. Once they have same temperature, there is no net heat transfer, and that condition is said to be thermal equilibrium. And the final temperature of the two systems become T, and this T, the final temperature of the system, is greater than T2, the smaller temperature, and less than the larger temperature. This state is known as thermal equilibrium. By thermal equilibrium, the two systems do have same temperature. Let's go to transfer of heat. As I've said, heat will transfer from a region of high temperature to a region of low temperature. This heat transfer occurs by different mechanisms, and the mechanisms by which heat energy is transferred from a region of high temperature to a region of low temperature is known as conduction, convection, and radiation. Conduction heat transfer occurs when heat energy moves through a material as a result of collisions between the molecules of the material due to temperature differences. That means, if we have a conductor, and if we grasp one end of the conductor and let the other end of the conductor into the flame, heat will finally reach to our hands. The particles of this solid material are fixed in their position by a strong intermolecular force. But even though they are fixed in their equilibrium position, they oscillate about their equilibrium position. As a result of this oscillation, they have oscillatory kinetic energy, though it is negligible. Now, let's see how heat will flow from this part of the conductor to the other part of the conductor. Here we have particles. These particles first absorb thermal energy from this source, the heat source. As they absorb thermal energy from the heat source, their temperature will increase. As their temperature increases, their kinetic energy also increases. As a result of this increase in kinetic energy, the probability of collision with a neighboring molecule will increase. As a result, they collide with the neighboring molecule. During collision, they become in contact. And during contact, since they have different temperatures, heat will flow from the hot molecule to that of the cold molecule. In turn, the molecule that absorbs thermal energy from the hot molecule will acquire high amount of energy as a result of increase in temperature. As a result of this acquired energy, the vibrational kinetic energy of the molecule also increases. As a result of this increase in vibrational kinetic energy, the probability of collision with a neighboring molecule will also increase, and they collide with the neighboring molecules. As a result of this collision, heat will flow from the hot molecule to the next cold molecule. In turn, this cold molecule will have thermal energy from the hot molecule and increased kinetic energy. As a result of this increased kinetic energy, the probability of collision with the neighboring molecule also increases. By these mechanisms, thermal energy will move from this part of the conductor to this part of the conductor. And here, the type of heat transfer, the mechanisms of heat transfer is conduction, and this conduction heat transfer results due to the collision of adjacent molecules of a solid material as a result of difference in temperatures. How can we measure the rate of heat transfer from this part of the conductor to the other part of the conductor? Let's consider a slab of material, say this slab, and the length of this slab or the thickness of this slab is delta L. The cross-sectional area of the slab is A, and this part of the conductor or this face of the conductor is T1, and the other face is maintained at T2. If T1 is greater than T2, energy will be transferred from phase 1 to phase 2. Heat flows from phase 1 to phase 2. The rate of heat transfer by conduction is the quantity of heat transfer per unit time delta T is proportional to the cross-sectional area of the slab, the temperature gradient delta T by delta L, where delta T is T1 minus T2 and delta L is the thickness of the slab. This is the same as the rate of transfer is equal to delta Q by delta T. The quantity of heat transfer per unit time is equal to minus K times A times delta T divided by delta L, where K is thermal conductivity of the material. Here the negative sign shows that heat flows in the direction of decreasing temperature. The negative sign shows heat flows in the direction of decreasing temperature. In other words, we can also determine the thermal resistance of the material. Actually, the rate of heat transfer here is directly proportional to the thermal conductivity of the material, the cross-sectional area of the material, and the temperature gradient. If the temperature gradient is large, the rate of heat transfer is large. To maximize the rate of heat transfer, the temperature gradient has to be large. If delta T by delta L is large, then rate of heat transfer is large, or delta Q is large. To increase this temperature gradient, either delta T has to be large or delta L, the thickness, has to be minimized so that the rate of transfer will increase. In terms of the thickness of the material and the thermal conductivity of the material, we can define thermal resistance. Thermal resistance R is equal to simply delta L divided by thermal conductivity K. The thermal resistance of a material is defined by the thickness of the material divided by the thermal conductivity of the material. If the thermal conductivity of the material is large, the thermal resistance becomes smaller. Resistance means an opposition to the flow of something. Here, thermal resistance is an opposition to the flow of heat. Therefore, if the conductivity is large amount of energy, thermal energy will be transferred. If thermal resistance is small, large amount of energy will be transferred. Therefore, to decrease thermal resistance, we need to increase thermal conductivity of the material. Therefore, thermal conductivity and thermal resistance are inversely proportional to each other. And this is the first mechanisms of heat transfer. The second heat transfer is known as convection heat transfer. Unlike that of conduction heat transfer, in convection heat transfer, heat energy moves through a material as a result of the actual movement of the molecules of the material through a large distance. There are actually two types of convection. One is natural convection or free convection, and the other is forced convection. In free convection, heat will transfer due to the difference in densities of the material. Assume here we have water. If this water is placed on a flame, the water molecules near the heat source will absorb thermal energy. Assuming that water droplets are spherical in shapes, as they absorb thermal energy, these molecules, when they absorb thermal energy, the volume will increase. As the volume increases, density will decrease because density is equal to mass over volume. Mass of the molecules cannot be altered even though the volume will increase as a result of this thermal absorption. Therefore, the density of the molecules near the heat source will decrease. Since the volume increases, the density will decrease. As a result of this decrease in density, they will float to the upper part of the fluid. And the fluids that are slightly denser than that of the fluid near to the heat source will move down to the source. Again, the molecules that come to this point will absorb thermal energy. As a result of this absorbed thermal energy, the volume will increase. Due to this increase in volume, the density will decrease and in turn they float to the upper part of the fluid. By these mechanisms, convection current will be produced and heat will transfer from one part of the fluid to the other part of the fluid. This kind of heat transfer occurs due to the movement of the molecules of the material through large distance, unlike that of conduction heat transfer. And this natural convection or free convection occurs due to density difference. As I have said, the molecules near to the heat source will absorb thermal energy. As a result of that absorbed thermal energy, their density will decrease and they float to the top part of the fluid, and the fluid with denser density will move to the bottom part of the container. Again, they absorb thermal energy. As a result of this absorbed thermal energy, the density will decrease and they float to the top part of the container, and by this, heat will flow from this part of the system to this part of the system. And this natural convection or free convection occurs as a result of difference in densities. The other type of convection transfer is known as forced convection. In forced convection, unlike that of natural convection, heat will flow from one part of the system to the other part of the system as a result of the external force. If we want to warm our room, then we need to let hot fluids to circulate around the building. To let the fluids circulate around the building through the pipe, we need to have an external source that can drive the water through the pipe. And such kind of heat transfer is known as forced convection. The third type of heat transfer is known as radiation heat transfer. In radiation heat transfer, energy will be transferred, or thermal energy will be transferred by means of electromagnetic waves. Consider this electrical stove known as Ethiopian injera method. This Ethiopian injera method will be a kind of stove. If we plug the power cable to the source and touch this electric stove, heat will be transferred to our hands by conduction. If we hold our hands above the electric stove, heat will reach our hands by natural convection or free convection, because between our hands and that of the stove there are air molecules, and these air molecules, when they absorb thermal energy from the source, their density will decrease. As a result of this decrease in density, they will flow to the top part of the air layer, and by this mechanism heat will reach our hands. But what if we hold our hands on the side of the stove, either here or here? Again, still, if we hold our hands here, we feel heat. How can this heat transfer occurs? It's not conduction, because our hand is not in contact with the source. It's not convection, because our hand is not above the stove. But this is due to radiation heat transfer. In general, let's consider this system. When this system gets heat from the external heat source, we have different mechanisms of heat transfer. One, if we touch the system with certain conductor, after some time heat energy will reach our hands, and this is known as conduction heat transfer. If we hold our hands above this surface, heat will reach our hands by natural convection or free convection. But if we hold our hands by the side of this system or below this system, energy will reach our hands, and this energy transfer is known as radiation heat transfer. Therefore, in general, today we have seen about heat and mechanisms of heat transfer. Next time, we'll see quantity of heat and specific heat capacity.